talk about AIC and BIC, the AIC information criteria and the Bayesian information criteria. These are famous variable selection techniques. So we'll talk about variable selection techniques used in econometric modeling. These are also useful in machine learning model building. So if you're a data scientist, you also will find these techniques quite useful. So what is variable selection? Well, it's the selection of the important variable in a regression model. So in a regression problem, actually you have quite a few, actually too many explanatory variables to start with, but not all of them are important for your regression model. You need to select the best set of variables important for your regression models, and for that you need to select which ones are the best, and that's variable selection is all about. Okay, in other words, we can also say that it's a way to drop the not so important variables. So that's other way to put it. Now, often there are the several numbers of variables that you will start, especially in the industry. Well, in academia, it's not that of a big problem, although it is indeed a problem there. But in industry, in industrial problems, you have just too many explanatory variables, and you can't build a model, let's say, with 100 variables, right? In econometrics, well, in machine learning, you can indeed build such models, but there also, it could tend to have problems if you just include as many variables as like hundreds of cases. So in econometrics, you simply cannot build such a model, right? That's not possible. Now you could run into problems if you actually use just too many variables. One is overfitting. So what is overfitting? Well, it's a problem in econometrics and machine learning models, wherein the model actually fits well for the given data, the data that you have used for training purpose, but the model will not do well in a new data set in the future. And that happens when you have too many variables in your model. When you have too many variables in a model, together they may do a good job in predicting the target or the response variable, but that is just for that particular data set or the training data set or the data set used for model development. But if you use that model in a new data set in the future, right, then it's not going to be performing well. And that's the problem, because we build a model for future use, and if it doesn't perform well in the future, then there's no point in building such a model. Hence overfitting should be avoided, and one big reason why we should be using variable selection technique. The other one is underfitting. Now this is quite pronounced in econometrics world, but not so much in the machine learning world. Because in econometrics, when you build models, you build model not just for prediction purpose, but you also build model to understand the relationship between explanatory variables and the response variable. And if your model has just too few variables, they're not, you have some missing variables, they're just too few variables, and the most important variables are missing from your regression model, then you will encounter an issue called underfitting. But there is also a technical term for that, which is called omitted variable bias. That means your estimates will be biased because some of the important variables are missing from your model. Now in that case, it is less of a concern if your intention is just to predict the outcome or the response. But if you are interested also in understanding the relationship, I mean, you are interested to understand, if your independent variable goes up by 1%, what will be the corresponding change in your response variable? Then in that case, you'll have trouble actually, and that's one reason why we build econometrics model, and that's an issue, and hence variable selection is also important there. We'll take an example. So we have this quadratic equation model, y equal to 1 plus 0.5x plus 4x square, and we'll fit this to a data, and here is this data, and as you see, it fits the data pretty well, right, as it seems to be the case. Now we will talk about two cases here. One is overfitting, the other one is underfitting. Okay, now to this quadratic model, we will try the data that seems to be fitting a quadratic curve, we will try to fit a linear curve. Okay, and in the second in the second point, where we are trying to fit a polynomial curve. Okay, so one will underfit, the other one will overfit, and here is this example. Here you see that this the green line, which is straight line, is underfitting the data because it is fitting. It's not as good a fit as, let's say, the red curve, right, which is quadratic. Whereas this dark blue line, right, the dark blue line here, you can see my cursor here, is overfitting. That means it is fitting wonderfully well for this data, but when you use that model for future, that will not work very well. So the second line, which is a 6 polynomial curve fit, if we go back to theory, here we have used y equal to x to the power 6, and that's doing a bad job if you just add too many parameters. So instead of just having x to the power square, what we started with, right, we started with x to the power square, that means the second polynomial, and we added x to the power q, x to the power 4, and x to the power 5 and 6. All that when added, it fits the data well, but it is going to do a bad job in the future because it seems to be overfitting. Now some of the points to note, that's what I have discussed, so not to spend more time here. It's important to understand the different uses of regression model. Now this might, the people coming from machine learning background, data science background, will find it bit somewhat different actually, because in econometrics, when models are built, they're not built just to predict the response variable or the target variable. You also build model to understand the relationship between variables, between explanatory variable and the target variable. That's not always the case in machine learning. In fact, that's not almost never the case in machine learning, where it's always predicting the target variable. That's the only intention. And from a variable selection point of view, this is very important to understand this, because if you are aiming to also see or explore the relationship between variables, the variable selection techniques will be somewhat different actually. Okay, and let's get into the details of how you can use variable selection in order to avoid underfitting as well as overfitting, and in the context of econometrics. But as I told you, it's also going to be very useful for people working in data science, machine learning, such fields. So alright, so how do we select the variables? Suppose we have, let's say, k number of variables. So how many number of so if we take all kinds of possible sets or subsets of variables, we'll be having 2 to the power k minus 1. So these many models, right? So imagine you have 10 variables in place. So how many number of models we'll have then? If we try every possible combination, then we'll have 2 to the power 10 minus 1. That's a massive number of models, right? And then choose the one which is the best model, right? So that's not a very good idea actually. It's very time consuming and also computationally very intensive. So there are better ways to do it. Okay. And the other way is to use some metrics and select the best model, right, where you can save on time and computational power. So all possible regression, right, all possible combination of the variables, and see where you get the best model, right, based on some criteria obviously. It has a lot of course, this way you can actually get to see all possible models, and it gives a lot of insight about the models, but the problem is that it's very time consuming and computationally intensive, right? And what criteria you will be using? Well, you can use R square. In regression, R square is a very famous metrics used to assess performance of how good the fit is, so goodness of the fit as you call it. yeah, you can also calculate adjusted R square. So it's slightly different from R square. You can basically you can just do a Google search what's adjusted R square. It is more of an adjusted form of R square, but nothing different. It's very close to R square. So R square is something that's used for selecting the best model out of this possible combination. You can also use residual mean square, which is the residual sum of square divided by n minus p. N is number of observation, p is number of variables used here, right? So more number of variables means it will penalize, right? And we'll see actually in metrics where in AIC and BIC these RMS is used. Residual mean square is actually used. Okay, so AIC and BIC. Okay, one is AIC information criteria and the other one is the Bayesian information criteria. So these are criteria that balances goodness of fit against the model complexity. That means if the model is too complex, then it will penalize for you, right? So it will penalize you for having just too many variables. What do you mean by a complex model? That means a model that has too many explanatory variables. So how do we calculate the AIC? So AIC is calculated like this. AIC is equal to n log of RMS plus 2p. Now we have defined what RMS is here, right? So it's the residual sum of square. So residual sum of square is nothing but your y minus y hat, okay, and just square it, right? That's, and take a summation of that. Your n log RMS plus 2p. That means if the p is more, p is basically number of variables here, and n is the number of observation. If the number of variables increases, then this will penalize us, right? And the AIC will be more. And the criteria is that if the AIC is less, that's a better model, and AIC is more, that's not as good a model as the one with less AIC. Alternatively, we can use the Bayesian information criteria, and look at my cursor here. Okay, so it's basically RSS divided by RMS plus p log n. Now here also you see in the second term you have p. That means if the p value is more, that means the number of variables are used more in the regression, then it will penalize, and hence the more the p is, the bigger the BIC will be, and a bigger BIC is actually not good for the model. The smaller BIC or smaller AIC is actually a good, indicates that the model is good and less complex, and that's something to be used. Okay. Now if you use all kinds of combination of explanatory variable, you can obviously just look at R square, AIC and BIC and see where actually you get high R square and low AIC BIC. The one that gives high R square and low AIC BIC is the one to be selected, that you can judge yourself. But you can also use other metrics such as prediction error, and this is very popular in machine learning world, where you basically see the difference of the error, and where you see the lowest error, you take the sum of square of that, and that's the one you use. But sometimes you tend to overlook the fact that there are too many variables or too many explanatory variables in your model, and through AIC BIC with combination of that, it actually helps you to get rid of some of these variables. Yeah. Okay, so cross validation is something, again, is a concept from machine learning, but is also now being increasingly being used in econometrics modeling. Now oftentimes what happens is that econometrics can actually use this same training data set to build the model and also test their model, right? That's not always a good thing. You should split your data set into two parts, preferably 70-30 or 60-40%. You build a model in 60-70% of your data and test in the other 30 or 40% of the data, right? That's basically known as cross validation. There are various techniques. This is just one way of doing it. There are many techniques. You can have more number of test data sets, not necessarily just one, but I won't go into details of it, but you can watch one of my video. I'll give in the description about cross validation and the different ways you can cross validate your model. So that's something you can watch to learn more about cross validation. Here also you can use, and econometrics also you can do that. You can have your R square, AIC and BIC, not just on training dataset but also on test dataset. And the one where you see a consistent values of your R square, AIC, BIC is the one to be used. Okay, so for example, you have high R square in training dataset but low R square in test dataset, then that's not a good model. So ensure that the R square value is consistent. So is AIC, BIC. So you may have low AIC, but ensure that these matrices are consistent across training and test dataset. Otherwise, you are not selecting the best model. As I said, for cross validation, you have many ways to do cross validation. That means you can have not just one test data set, but you can also have more than one test data set. So for example, you have 10 cross validation, 5-fold cross validation. That means 10-fold cross validation means you have 10 test data sets and you check your model performance in each one of them. Okay, and just then see, because if you just check in one of them, one data set, it could give you misleading results. And when you take 10 of them, not separately, but it's randomly selected from this sample, then it could give you more confidence. So it's somewhat different, but yeah, it's a more foolproof one. You can watch this video on the link to learn more about that. Now we'll take an example. So here is this example where we have quite a few variables on the evaporation data. As you see, there are some 10 to 12 variables, and we select some of the important variables. Okay, so what we do is that we basically use R to find out the coefficients of the regression. We use all of them, all variables. As you can see, some of them, like yeah, so the ones marked in red and with star are the significant ones. So by looking at the p-value where you see less than 0.05, it's significant at 95% confidence level. So 3 important variables. Okay, we have R square, which is 84%. Adjusted R square is 80%. Normally adjusted R square penalizes you for having more number of explanatory variables, and it's always less than the R square value. Okay, so these are 2 important metrics to look at, and also the significance value of each of these explanatory variable, right? And then we also try to find out the other matrices, for example the AIC, BIC, and the cross validation error rate. Okay, now as I mentioned a couple of slides back, that the one with lowest AIC, lowest BIC, and highest R square and lowest cross validation error is the one to be selected. Okay, so here you see that and these are basically your iterations, right? Iterations means we started with 1 variable, then we start with 2 variables, 3 variables, 4 variables, 5 variables, 6 variables. Okay, so you take all combinations. So in the first case, you see only this particular variable has been used. Second case, this max h and max at has been used, so 2 variables, right? And for each one of them you have AIC, BIC, and CB. And here you see the AIC value is actually okay, so basically you have to check the cross validation error and the R square. So R square is here, and you see the R square value increasing with more number of variables. So as you increase the number of variables, you see the R square increasing from 67% with just 1 variable. It went to 80% with 4 variables and 81% with 7 variables. But after that, if you start increasing more number of variables, then there is no increase in the R square, right? The BIC, AIC and BIC, as I told you, the AIC, BIC should be less actually. Less is better, and cross validation errors should also be less. And here you see the cross validation is in 191, which is the lowest among all these cases, right? And you get 79% R square, which is slightly like 0.2% less than the maximum, which is still okay, right? And you see also quite low AIC, BIC. You also have lower AIC next model, but I think you still have quite low AIC. That means that with 3 variables it works fine, right? So the third case where you have max at, max h, and win 1. So that's the way to select the best set of variables for your model. Now, for econometricians normally don't look at the cross validation error, but I highly recommend you to have a look at that, right? So that actually helps and also makes your research work more foolproof. And then what you do is that with these three variables, you re-estimate your model again. And interestingly, you see the R square value is now 80.5%. Now, when we started with some 12 variables, what was the R square? It was 84%. Now there is a decrease of 80%, but it is not overfitting. So that extra 4% was more like overfitting. That means in the future data, there is no guarantee that your accuracy rate or the it's not accuracy, but R square is about your ability of the explanatory variable to explain variation in the target variable is 85%. That's not the case here. It could be completely wrong in the future data because 12 variables are overfitting the model, but with less number of variables, with these three most important variables, now you get an accurate value of the prediction ability of the model or the goodness of the fit of the model. Now, most importantly, now the estimates are also better. So here you see this estimates, right? Beta estimates, these are also better, right? And if you really want to understand the relationship, to what extent if you increase max H, how much will be the impact on the target variable. So just by looking at this estimates, is 34%, 0.34, you can actually explain that. For people coming from machine learning, it does not make much sense because they're not interested in that. But econometricians, especially working in policies and such things, where explainability is also quite important, this matters a lot for them. Thanks.